Hello and welcome everybody. My name is Elliot, and in this physics mini lesson, I'm going to show you how to derive the equation for the orbit of a planet like Earth around a star like the Sun, or even something like a comet that's just passing through the solar system, using Newton's inverse square law of gravity. In my last video, I showed you how you can very quickly understand the general shape of an orbit just by drawing a picture called the effective potential. But in this video, we're going to get into all the nitty-gritty details and actually derive the equation for the orbit. As usual, I've written up notes which you can pull up if you like, and I've also posted a problem sheet which you should try after you've watched if you really want to understand all this. I think this is pretty incredible. People have been gazing up at the sky for all of human history trying to understand our place in the universe, or even just our place in the solar system for that matter. But it wasn't until around 500 years ago when people like Copernicus, Brahe, and Kepler firmly established the elliptical orbits of the planets in our solar system by collecting meticulous data. And it was Isaac Newton who explained those observations with a mathematical model. And that's what we're going to reproduce in this video. With really just a few lines of math, we're going to derive the orbit of our home planet around our star. So I hope you're excited to see this worked out, especially if you've never seen it before. And without further ado, let's dive into it. Here's the setup. We've got a star like the Sun and a planet like the Earth. Say the star has mass big M and the planet has mass little m. We're going to treat them both as point particles for simplicity here. Let's put the star at the origin of our coordinate system, and say the planet is some distance r away. Then, according to Newton's law of gravitation, there's going to be a force on the planet of magnitude big G, big M, little m over r squared. And the force is pointing back toward the star at the origin. Big G here is the gravitational constant, which is what measures the strength of the gravitational force. This quantity, big G, big M, little m, that's going to be showing up a lot, so it's useful to define a shorthand for it. Let me call it little k. Of course, there's also going to be an equal but opposite gravitational force on the star pulling it toward the planet. But assuming that the star is much more massive than the planet, the same force that caused a big acceleration of the planet doesn't have much effect at all on the star. For the Earth and Sun, for example, big M over little m is around 3 times 10 to the 5th, meaning that the Sun is around 300,000 times more massive than the Earth. So that means it's a good approximation to say that the star just remains at rest at the origin. Say that the planet is at some position r and with velocity v. Then the question we want to answer is, what path is it going to follow as time goes on? Let's set up our coordinates so that r and v both lie in the xy plane, at least initially. Then the first thing to notice is that the motion is going to be confined to the xy plane. In other words, if the z-coordinate of the planet was 0 when t was equal to 0, then it's going to remain 0 forever. This remarkable property arises from the fact that the gravitational force only depends on how far the planet is from the origin. Beyond that, it doesn't matter if the planet's to the right or left or top or bottom of the star. Only the distance r matters. Said differently, the force is spherically symmetric. The basic reason that this means the planet will be stuck in the xy plane is that at t equals 0, the position, the velocity, and the force are all pointing in the xy plane. Nothing points or is any component at all in the z direction. Say the planet did leave the xy plane at some time after t equals 0. Which direction would it go in? Along plus c or along minus c? We have complete symmetry here between the plus c and minus c directions, so the planet can't pick one or the other. It has to stay in the xy plane. For a more mathematical proof of this fact, let's define the angular momentum vector L by m times r cross v. Let me explain this in case you haven't seen it before. First of all, mv is the momentum of the planet. So the angular momentum is the product of the position vector and the momentum vector. But it's a very special kind of product. The x here stands for the cross product of the two vectors r and v. Let me draw them over here to explain what that means. So here's our position vector r and our velocity vector v. Again, both of them are in the xy plane. First of all, the cross product of two vectors gives you another vector. and its direction is perpendicular to both of the vectors that you started with. So since r and v were both in the xy plane, their cross product points in the z direction, coming out of the page here. As for the magnitude of the cross product, let's drop a little perpendicular line from the velocity vector to the position vector. Write down the length of the perpendicular leg here. Call it v sub perp. Then the length of the cross product, by definition, is the length of r times the length of that perpendicular component of v. So that means that the angular momentum is m times r times v perp, pointing in the z direction. Now, if you've never encountered angular momentum before, it might seem like a peculiar definition. So why is this physically useful? Well, for the moment, it's useful because it's a constant for the planet. We can check that pretty easily. Let's just take the derivative of L with respect to time. The things that depend on time here are the position r and the velocity v. The rate of change of r is just the velocity again, and the rate of change of v is the acceleration a. We need to remember to apply the product rule, so we're going to get two terms, mv cross v plus mr cross a. I claim that both terms vanish here because of the definition of the cross product. Remember that the length of the cross product of two vectors is proportional to the perpendicular component of one vector along the other. So notice that if two vectors are parallel or antiparallel, in other words, if they're pointing along the same line, there is no perpendicular component of one along another, and so the cross product vanishes. Well, v is obviously parallel to itself, so there's no perpendicular component, and v cross v is equal to 0. As for the second term, notice that m times a is the force on the planet. But according to Newton's law of gravity, the force is pointing along the radial line from the star to the planet, which is parallel to the position vector r. Therefore, the second term also vanishes, and the rate of change of the angular momentum is 0. So L is indeed a constant. But now how does that show that the motion of the planet is confined to the xy plane? Well, again, the definition of the cross product says that L is perpendicular to both r and v. That since L is constant and always pointing in the z direction, r and v always have to point in the xy plane if they're going to remain perpendicular to L. So the planet is stuck in the xy plane, and that's a huge simplification. Instead of having to solve a fully three-dimensional problem, we only have to solve a 2D problem. So we want to figure out the path that the planet follows in the xy plane. And we're going to use the fact that L is constant. But that's not the only thing we know that's constant. Of course, there's also the energy of the planet. That's 1/2 mv squared plus the potential energy U. Since the planet is moving around in the xy plane, there's two components to the speed here. There can be a radial piece, dr by dt, and there can be an angular piece. The angular piece is just r times d theta by dt, where theta is the angle that the planet makes in the xy plane. And that's just the familiar formula v equals omega r from circular motion, where omega is the rate of change of theta. So plugging those back into the energy, we get 1/2 m times the radial speed squared plus 1/2 m times the angular speed squared plus the potential, which is minus k over r. Well, remember, we defined k equals big G, big M, little m for short. Notice that the angular velocity here is what we called v perp before. It's the component of the velocity that's perpendicular to the radial direction. So that means that the angular momentum is m times r times the angular velocity, which is r d theta by dt. That's a remarkable formula because it says that if we know the radius of the planet, then we automatically know what its angular speed is. D theta by dt equals L over mr squared. And we can use that fact in our formula for the energy to replace the second term by L squared over 2mr squared. The reason that's useful is because it eliminates all the thetas from the energy formula and writes it entirely in terms of r. Then our energy looks like the standard energy of a particle moving in one dimension with coordinate r. Except that the potential is not just the gravitational potential. There's this extra term L squared over 2mr squared that's added to it. We call this combination the effective potential. And in my last video, I showed you how we could use the shape of the effective potential to predict the shape the orbits will take just by drawing the picture of the effective potential. If you want to learn how that works, you should watch that video if you haven't already. Again, I'll link it up in the corner. Okay, at this stage we have two equations. One for d theta by dt from the angular momentum L, and one for the energy as a function of r. But I want to rearrange this energy equation to solve for dr by dt. So we can write it as dr by dt squared equals 2e over m minus L squared over m squared r squared plus 2k over mr. So these are two differential equations for r of t and theta of t. But actually, we're not too interested in the t dependence here. What we really want to know is the shape of the curve that's traced out by the planet. In other words, we want to know r as a function of theta. And we can actually get rid of all the t's by dividing these two equations. Because dr by dt squared divided by d theta by dt squared, the dt's cancel and you just get dr by d theta squared. So now we're left with a differential equation with no t's anywhere. We've got L over mr squared, all that's squared, times dr by d theta squared equals 2e over m minus L squared over m squared r squared plus 2k over mr. Now that's looking a lot better. It's a differential equation for r of theta, and in the home stretch here, we just need to solve it to figure out the path that's traced out by the planet. To solve this equation, the first thing we should notice is that all these r's are in the denominator, which means that it might be easier to solve for 1 over r instead. So we're going to make a change of variables and let u equal 1 over r. And I'm also going to throw in a factor of L squared over km out front, which is going to make our equations look a little bit simpler. So let's plug this change of variables into our differential equation. First of all, it also says that r equals L squared over km times 1 over u. And so dr is equal to minus L squared over km times 1 over u squared times du. Now we want to plug these formulas into the differential equation. After a little bit of simplifying, which I'll leave for you to do on your own, I get u prime squared equals minus u squared plus 2u plus 2el squared over mk squared. That's already looking a bit simpler, and now we want to integrate this equation to figure out u as a function of theta. But actually, it's easier to solve this equation if we first take another derivative. Because if we do that, we'll get 2u prime times u double prime on the left equals minus 2u u prime plus 2u prime on the right. And now we can cross out those factors of 2 and the factors of u prime, and we get a really simple equation for u double prime. It's u double prime equals minus u plus 1. Compared to where we started, this is a super simple equation. We just ask ourselves, what kind of function, when I take its second derivative, gives me back minus that function plus 1? Well, except for that 1, the answer would be a sine or a cosine. And then to account for the shift by 1, we just have to add that on to our solution. So in other words, u equals epsilon cosine of theta plus 1 will solve the equation, where epsilon here is an integration constant. Let's check. U double prime just turns into minus epsilon cosine of theta. And indeed, that's the same thing as minus u plus 1. Again, this epsilon is an integration constant. And I called it epsilon instead of something like a or b, as you'll see in a second, because it's going to have some physical significance. To figure out what epsilon is, we need to plug our expression for u back into the original equation for u prime squared before we took the derivative. First of all, note that we can simplify the right-hand side, as 2el squared over mk squared minus u times u minus 2. And that makes it really easy to plug in our expression for u. We get 2el squared over mk squared minus epsilon cosine of theta plus 1 times epsilon cosine of theta minus 1. And now if we expand that out, we'll have minus epsilon squared cosine squared plus 1 on the right there. Now on the left-hand side, remember we had u prime squared. Well, u prime is equal to minus epsilon times sine of theta. So the left-hand side is epsilon squared sine squared. And we have a sine squared on the left and a minus cosine squared on the right. So when we put those two together, we're going to get epsilon squared all by itself on the left. And at last, we can solve for epsilon. It's given by 1 plus 2el squared over mk squared square root. Well, now we're essentially done because we've solved for u as a function of theta equals 1 plus epsilon times cosine of theta. But r, remember, was just equal to 1 over u times a constant. And so we can finally solve for r as a function of theta. It's given by L squared over Km times 1 divided by 1 plus epsilon cosine of theta. And there we have it. This is the equation for the curve that's traced out by the planet as it travels around in its orbit. So what the heck is this thing? Well, it's called a conic section of eccentricity epsilon. And you may have learned about conics before in your math classes, but they're shapes that include circles, ellipses, parabolas, and hyperbolas. And the different kinds of shapes are labeled by this parameter epsilon. Epsilon equals 0 is a circle. When epsilon is between 0 and 1, that's an ellipse. When epsilon equals 1, that's a parabola. And if epsilon is greater than 1, that's a hyperbola. And the easiest way to see what this looks like is just to plot r of theta and see how the curve depends on epsilon. So here's an animation to show you what this looks like. I'll link it below if you want to play with it. This slider for epsilon controls the eccentricity. Remember, epsilon equals 0 is a circle, and then as you ramp up epsilon, it kind of measures how much you've deformed away from a circle. So when epsilon is between 0 and 1, that's an ellipse. Notice that the sun is not at the center of the ellipse. It's at a focus point. Now if I crank it up all the way to 1, I get a parabola. And beyond epsilon equals 1, the shape is a hyperbola. Now let's dial it back down to a circle. If I press start here, what this animation does is numerically solve the f equals ma equations to determine the orbit as a function of time. And when epsilon equals 0, the planet is just going around in uniform circular motion. Now if I increase epsilon a little bit, the orbit becomes elliptical. And the speed of the planet is not constant anymore. You can see that it's slowest when it's farthest away and fastest when it's closest. That's because the angular speed, remember, went like L over mr squared. Now if I crank epsilon up even more, the trajectory becomes the hyperbolic path of something like a comet that slingshots around the sun. For the orbits of the planets in our solar system, they are elliptical, but maybe not as much as you might think. Earth, for example, has an eccentricity only of around 0.02, which is only slightly non-circular. Mercury has the largest eccentricity of all the planets at around epsilon equals 0.2. But even that is only slightly non-circular to the naked eye. The orbit of Halley's Comet, by contrast, is around 0.97, which is about as elliptical as it gets. So there we have it. With really not all that much work, considering the huge significance of the result, we've derived the equation for the orbit of our home planet around our star. And if you try the problem sheet out, you'll get some practice applying this machinery to the orbit of a flying saucer around the Earth. Finally, you should know that Newton's inverse square law is not the last word on gravity. It's very effective for predicting the orbit of a planet that's relatively far from a star. But as you get closer and gravity gets stronger, Newton's theory becomes less accurate. For Mercury, for example, the closest planet to the Sun in our solar system, the orbit is not a perfectly closed ellipse. Instead, it precesses ever so slightly, which means that with each revolution around the Sun, Mercury's point of closest approach occurs at a slightly different angle. The precession of Mercury is explained by Einstein's theory of gravity, general relativity, which extends and supersedes Newton's inverse square law. And one day, Einstein's theory will be supplanted by a quantum theory of gravity, which is a mystery that physicists have been trying to unravel for a century. So that's it for this video. Links to the animations, to the notes, and the problem sheet, all that'll be down in the description. Please hit the like button, subscribe to the channel, and leave any questions down in the comments section or suggestions for other topics that you'd like me to cover in the future. Thanks for watching, and I'll see you next time.